Okay, I'd just like to say welcome, everybody. We seem to have a very interesting speaker this evening. Well, quite often, most of the time we do. Yeah, I look forward to it, and I'm going to ask Peter Kotze to introduce Peter Meintjes because he knows him well.
Yes,
Thanks.
good evening, everybody. It's a great pleasure to introduce to you tonight Piet Meintjes. I've known him for quite a number of years. He's currently professor in astrophysics at the University of the Free State, and his focus of his research is on the high energy emission of compact objects like neutron stars, which will then also form the main focus of his presentation tonight. So Piet is a very well-established, international acclaimed researcher, and I'm sure everybody will enjoy the talk that he's going to give tonight. So Piet, thank you very much. Over to you.
Thank you very much, Peter. I really appreciate also this invitation. So I hope this presentation will be interesting and give all of us something to think about. So the topic of the presentation is cosmic power stations, and I thought that was sort of quite a relevant topic in the sense that we are struggling ourselves here in South Africa with our power stations, given that we are sort of working now through level 6 of load shedding. But I'm going to show you power stations in space, and that is fast rotating compact magnetized stars, especially neutron stars and white dwarfs, and the high energy emission that these systems can produce. I'm going to end off this presentation by just show you some results of high energy emission from white dwarfs. That is a little bit closer to my research, and hopefully that will also show you that what we are talking about this evening is not just theoretical concepts, but that we actually see and detected the high energy emission from these fascinating objects. So the layout of the presentation is something like that. I'm going to show you all just basically sort of the broad family picture of stars in terms of the Hertzsprung-Russell diagram, different kinds of stars, give you a brief overview of stellar evolution in terms of how do we get to these compact neutron stars and white dwarf systems. And then I'm going to explore a little bit the physics around these compact objects. I'm going to talk about the pulsars and neutron stars and white dwarfs and show you some of the latest research results that we have obtained. And hopefully that will convince you that these are really fascinating objects. So obviously, if we are talking about stars, our familiar example is our beloved Sun, which is a average G-type star. And it's not even a big star in the Hertzsprung-Russell diagram. That is what I call the family picture or family portrait of stars, which is just a diagram which expresses the luminosity versus surface temperature. So on the Hertzsprung-Russell diagram, you can find the Sun somewhere over there. And I can just explain this diagonal line is all the stars that are burning hydrogen into helium in their course. And the Sun is also on the main sequence, burning hydrogen into helium, and it will still do so for the next 5 billion years or so. And then obviously, as you move to the upper left of this diagram, you get the enormous blue O and B type stars, and they are running through their nuclear processes at a rapid rate. Obviously, enormous hot cores where hydrogen is fused into helium, and some other processes also taking place, and nuclear energy is produced at an enormous rate in these systems. After the hydrogen burning ceases, the stars move off the main sequence into the giant branch. And this is basically also what we are going to talk about a little bit, because both neutron stars and white dwarfs end up basically as stars that have evolved off the main sequence. And obviously, when the nuclear fuel is exhausted for these supermassive stars, you get a massive explosion, which is called the supernova explosion. But I will say more about that a little bit later. So just to show you some examples, the familiar constellations Orion and Scorpion that are now up in the night sky. Orion, our summer constellation, is now sort of setting quite early on the western horizon in the evenings, with the O-type star Rigel and Betelgeuse, the supergiant. And if you compare the size of Betelgeuse to that of the sun, that little white dot that you see there, you can see it's enormous. And also in Antares, in the constellation of the Scorpion, you can see Antares is even bigger. So these are two examples of stars that have moved off the main sequence, and obviously they have now entered the next phase of their evolution. And from these these red giant stars, depending on what the mass is, you can get either a supernova explosion or what we call a planetary nebula, from which you get a white dwarf star. But we will say more about that a little bit later. So just to conclude now in terms of stellar evolution, obviously stars evolve from molecular clouds. You first get a protostar, and depending on what the mass is, you can get a sun-like star for stars typically in the mass range of 1 solar mass or so. After the nuclear hydrogen is exhausted, the star moves off the main sequence, and then obviously it can enter a red giant phase, where it can at some point in that phase burn basically alpha particles or helium nuclei to form carbon and oxygen. And obviously when that is exhausted, you get enormous stellar winds that can drive away this outer envelope and leave behind that bright object there in the center, which is a white dwarf. These white dwarfs can have masses typically in a range of 0.6 solar mass, or let's say 0.5 solar mass, up to masses exceeding 1 solar mass, but not greater than 1.4 solar mass. Stars like the blue type supergiants can also enter a red giant phase, and depending on what the mass is, you can get a type 2 supernova when all the nuclear fuel is exhausted. I will say more about that a little bit later. And if the mass is very high, that the supernova explosion can leave behind a black hole. So I'm going to talk about these two sort of processes where the end result is a neutron star, and the other one is a white dwarf star. And I'm going to tell you a little bit about the physics that support these fascinating compact objects. So just to show you what the difference is between a supernova explosion, this is the familiar picture of the crab supernova remnant, where you have there right in the center of it a very hot object, very dense object, a fast rotating neutron star. The emission that you see in this supernova remnant is entirely the result of synchrotron radiation of fast rotating electrons that are trapped in these magnetic fields and producing synchrotron radiation. And obviously it is fed by that machine there in the core of this remnant, that fast rotating neutron star, which we call a pulsar, that accelerate electrons to enormous energies, and that electrons obviously populate and fill this supernova remnant, and resulting in this bright remnant that shines as a result of synchrotron radiation. Stars like the sun that end up in a planetary nebula, you can see there in the center that bright object with a surface temperature of a few times 10 to the 4 Kelvin, and with the nebula there around it that is ionized by the high energy emission, the ultraviolet and X-ray photons from that that object in the center, the white dwarf. So just basically to show us what the sun will do in its evolution. The sun obviously is now currently burning hydrogen into helium for the last 4.5 billion years. But over the next 5 billion years, the sun will leave the main sequence and move off into the giant branch to become a red giant. And if you want to compare the current size of the sun with the red giant that it will become in about 5 billion years, you can see there's an enormous difference in size. So this, in the red giant phase, the diameter of the sun will be basically 2 astronomical units, meaning that it will fill basically the whole inner part of the solar system up to the orbit of Mars, maybe even further. So in that giant phase, when it is becoming a planetary nebula, I can just show you what evolutionary path it will take in that phase of its evolution. Enormous winds will blow away this outer part of the envelope of that star. And as more of that envelope is blown away into space, more of this white hot object in the center will become visible. So you can see more of that inner object. So that is why the temperature will increase towards the left of this Hertzsprung-Russell diagram as you see more of that hot object in the center. But since you lose a lot of the outer layers, the luminosity remain more or less constant. But that is basically what will happen. And then when most of the outer envelope is blown away, it will just cool down and settle there on the Hertzsprung-Russell diagram, where you will find the population of white dwarf stars. Just some Hubble Space Telescope photos of these planetary nebula. It's always fascinating to look at with the hot white object there in the center, which is the central object or the white dwarf. So these white dwarfs, they are fascinating objects. So I do a lot of my research on these objects. So they are quite small compared to the original star. They have a size, a radius comparable to the radius of the Earth. A very hot temperature in the outer envelope, a few tens of thousands degrees of Kelvin. And they are very dense. Densities of the order of 1,000 kilograms per cubic centimeter. So you can see it's enormously high density objects. And therefore, as a result of this high density, the thermodynamics that occur there in the inner part of these objects are totally different from the thermodynamics that we know in normal gas environments like the sun, for example. But I will say a few words about that a little bit later. The brightest star in the night sky, Sirius A, has a very faint companion. You can see there in the glow of Sirius A, which is Sirius B, which is a white dwarf star. It is very small, much smaller than Sirius, but very, very hot. Temperature of about 10,000 Kelvin on the surface. But as a result of that small size, high mass, obviously it has an enormous gravity field. And I will say a few words about the gravity of these objects. Like I've mentioned, since these objects are very dense as a result of the high mass that is compressed in a very small space, all the electrons are squeezed into the lowest energy states. And we say that this results in a highly degenerate electron gas. And these stars are supported mainly by this degenerate electron population because all the electrons are squeezed into the lowest energy states. And obviously, gravity cannot compress this system any further. So this whole system is supported by that population of degenerate electrons that are all pushed into the lowest energy states. So gravity cannot compress them any further. For stars that have a mass greater than 1.4 solar mass, like neutron stars, it is not degenerate electrons that are supporting the star against its own gravity. As in that supernova phase where the star explodes and the inner core collapses, you get a very interesting process where the electrons are squeezed into the protons to become neutrons. But as a result of the high density, all these neutrons are also squeezed into the lowest quantum states. So therefore, neutron degeneracy pressure support these neutron stars against their own gravity. But obviously, if the progenitor star has a mass greater than 3 solar masses, then gravity wins overall. Not even neutron degeneracy pressure can stop that process. The gravitational collapse is just one way, and the end result is a black hole that will form out of that process. So let's look at this electron degeneracy pressure in these white dwarf stars. Now, that is what the sun will become at the end of its hydrogen burning evolution. So electron degeneracy is responsible for balancing gravity. And obviously, gravity is enormous because you have a small star with an enormous mass. So the mass is about the mass of the sun. The size is about 10 to the 7 meters or so. That is typically the radius of the Earth. So it means that the surface gravity is about 10 to the 6 meter per second square, which is about 100,000 times higher than surface gravity here on Earth. So you can see it is enormous. So this whole gravity is supported by this population of electrons that are squeezed into the lowest quantum states. And a typical pressure that you will get from this degenerate electron population is about 10 to the 22 Newton per square meter. So that is the pressure that supports this whole configuration against this gravitational force, because gravity wants to make this whole configuration collapse. So something must prevent that, and that is this this electron degeneracy pressure. You can see the electron density is enormous, 10 to the 36 per cubic meter. And that is basically providing this enormous pressure. The equation of state, the pressure inside these compact objects, depends on density to the power 5/3. So you can see, for those who can remember the ideal gas law from school physics or physical science, you can see this is definitely not the ideal gas law. The pressure depends only on the density of the material inside to that power. So this is the equation of state of this white dwarf, of such white dwarf stars. You can see that the pressure is about 10 to the 17 times normal atmospheric pressure here on Earth. So there where you sit in your rooms, close to the sea, the atmospheric pressure is about 100,000 Newton per square meter. You can see that this is about 10 to the 22 times higher, 10 to the 17 times higher than normal atmospheric pressure. So you can see that is enormous. And the pressure must be high to support this whole configuration against gravitational collapse. Just to show you a nice picture in the constellation of the Scorpion, which is now our winter constellation. If you go outside, you will be able to see the Scorpion rising in an hour or two's time. There you have the Messier object M4, and in that M4 you have an enormous population of white dwarf stars. All these white little specks there are just white dwarfs that have been observed by the Hubble Space Telescope. So if you go outside, if you can find M4 with a small telescope or binoculars, know that there inside in that cluster of stars, you will have also a huge population of these white dwarf stars. Sometimes these white dwarf stars find themselves in a binary system where you have a binary companion that can feed material to the white dwarf, and obviously as a result of that, you can get a mass accretion onto the surface of this white dwarf star that produces also enormous amount of radiation. So this is typically also systems that I study with my students, to study the processes of these binary systems, especially the mass transfer from these secondary stars, these companion stars, to the white dwarf. And Peter, I think you will remember, you have been external examiner of one of my students that I got from NASP many years ago, where we've modeled the magnetic fields of these secondary stars, because those magnetic fields have a dramatic influence on the mass transfer rate to these compact objects, and that obviously determines the emission that you can get from these systems eventually. Okay, so let's look a little bit about the more massive stars, like the O and B supergiant stars. These stars are so hot inside that they can run through all the nuclear processes, hydrogen burning, helium burning, nitrogen, carbon, magnesium, until you get a core there in the center that consists entirely out of iron. Now, the moment that such a massive star ends up with an iron core, no more energy production can occur through nuclear fusion, because the energy production, if you want to fuse iron into heavier elements, is not releasing energy, but it is consuming energy. So this is a nice diagram, one of the most important graphs in physics, the binding energy per nucleon as a function of atomic mass number. And you can see there where you get iron, that is the highest binding energy per nucleon, which means that iron is the most stable of all nuclei. And another way to explain this graph is just to look at the nuclear mass, the mass per nuclear particle in an atomic nucleus, which shows you that the mass per nuclear particle is the lowest for iron. And that is the reason for that is a lot of the mass of that nucleus is basically used as binding energy to keep that nucleus together, to make it a very stable configuration. So all the nuclear fusion reaction processes to burn hydrogen into helium, helium to carbon, carbon to oxygen, and also oxygen to magnesium, and also to end up with a nucleus of iron in the end. Those reactions produce energy. But if you want to use or to fuse iron into heavier nuclei, you run into a serious problem, because all those reactions are endothermic, meaning that they consume energy. You need an external source of energy, which there isn't, because the star has consumed all its nuclear energy. So obviously nuclear fusion stops. No more energy production occurs when the core consists of iron, and then that star has reached the end point of its evolution. So what happens then? I'm just going to go over this very quickly. When that occurs, when that core consists of iron, the density, obviously, there's no more nuclear fusion that can generate energy. So that core then starts to contract very rapidly. So very quickly, you end up in a situation where the electron density becomes so high that the pressure that you can get from electron degeneracy with that electron density reaches values of about 10 to the 27 Newton per square meter. But that is, although that is enormous, that is not enough to support that collapsing core against gravity. What happens then is basically there's an enormous amount of energy drains that occur in that last phase of that star's evolution. Because as that core collapses, and obviously, and that occurs at temperatures greater than 1 billion Kelvin, you get that the gamma rays that are produced through these nuclear reactions can break up iron nuclei to form, obviously, helium-4, plus, obviously, neutrons. But this process absorbs about 10 to the 44 joule of energy. If you think about 1 kilogram of iron absorb energy equivalent to 50 kilotons of TNT. For a 1.4 solar mass core, this drains in total about 4 times 10 to the 44 joule. Okay, so that energy is now obviously lost. I mean, that is energy that is consumed. And then obviously the contraction occurs even more. And when the core reaches temperatures of about 10 to the 10 Kelvin, the gamma rays obviously break up the helium to form protons and neutrons, and that drains another 10 to the 45 joule in energy. So that is an enormous amount of energy that is lost in this process. So obviously you can imagine now, since you have this enormous amount of energy that is drained away by these processes, nothing can really prevent that core from collapsing. And then as a result of the enormous densities, when this core collapses, you get the electrons that combine with the protons to form neutrons and neutrinos. An enormous amount of neutrinos are produced in this last phase of the collapse. And now about 10 to the 57 neutrinos basically fly away from these reactions. And since nothing can keep the neutrinos, they interact with nothing, they just move out of that hot core and drain this last bit of energy, about 10 to the 45 joule. And now you can see for yourself, as a result of this enormous amount of energy that is drained away in this process, nothing can prevent this gravitational collapse. And obviously this whole configuration basically implodes. And depending on what the mass of the progenitor star is, you can get a neutron star. So there are two types of supernova. The first one is now this one that I have mentioned, where you have a massive star that collapses when the core consists of iron, producing an enormous supernova explosion with a shock wave that blasts the system basically out into space. But you can also get a type 1 supernova where you have a binary system consisting of a star and a white dwarf. As a result of mass accretion, that white dwarf star can grow in mass until it reaches a critical limit, which we call the Chandrasekhar limit. And that Chandrasekhar limit is that limit where electron degeneracy cannot support that white dwarf anymore. The mass is about 1.4 solar masses, and then that white dwarf collapse in a type 1 supernova explosion and blowing all the system, basically all the material that have accumulated there on the surface out into space. But the type of supernovae that produces neutron stars or pulsars that I'm going to talk about in a short while is this type 2 supernova process. So just to show you the energy budget, the total gravitational energy that is released in this supernova explosion is about 10 to the 46 joule. And 99% of this energy goes into neutrinos, and only 1% into mechanical energy. And these neutrinos don't interact with normal matter, they just go right through. So obviously, that is why the whole configuration imploded in the first case, is that all this energy inside is basically carried away by neutrinos. The 1% that goes into mechanical energy obviously accelerates that envelope, that ejecta outwards. So if you have the total mechanical energy and the mass of the ejecta, you can see that the velocities are enormous, about 3,000 kilometers per second, that this nebula expands outward. So you can see it's an enormous amount of energy that has been ejected into this process, and you get this remnant that flies into space or outward into space with enormous velocity of about 3,000 kilometers per second. This is just basically some photos taken by the Hubble Space Telescope of some supernovas that occur in external galaxies. And you can see that although these galaxies are millions of light years away, some of them even billions, that the supernova explosion basically outshines the whole host galaxy itself. So you can see it's an enormous amount of energy that has been sort of released in these supernova explosions. So these supernovas are important for more ways than one, and that is that most of the heavy elements in the periodic table, like silver and gold, are produced in these supernova remnants and these supernova explosions. So they forge all the heavy elements like silver and gold and so on. So just to show you the periodic table, so these extremely light elements, hydrogen and helium, they were forged in the Big Bang, as far as we know. all the elements here up to iron, they were forged in nuclear reactions in stars. And all the heavier elements, like for example, the gold and silver and palladium and so on, and uranium, they are forged in these supernovae explosions. You may remember in 2017, there were two neutron stars that collided, and there was also a gravitational wave signature that we detected, but there was also a gamma ray signal. But the optical spectroscopy showed these enormous broad lines, and this is basically lines of rare earth elements that were forged in this collision process. So you can see that colliding neutron stars and also supernova explosions are extremely important to produce these heavier elements in the periodic table. So let's look at these neutron stars. So you can see that they are very compact. The size, well, 10 to 15 kilometers. Well, I think 10 to 15 kilometers is basically the size of a town like Hermanus or Bloemfontein for that matter. So it's extremely compact, but you have an enormous mass that is now compressed in a small sphere with a radius 10 to 15 kilometers. So the surface gravity on these objects is enormous, about 2 times 10 to the 12 meters per second square, which is about, if you look at this enormous number, 200 million times gravity here on Earth. So you can see it is enormous surface gravity. So obviously you need enormous pressure to support these systems against its own gravity. And the pressure is, in this case, provided by neutrons. Neutrons are formed in these objects, since in that implosion process, electrons combined with protons to form neutrons. There's also some neutrinos that were released, but these neutrons are all squeezed into their lowest energy states. So therefore, this degenerate neutron population, provides the pressure to support the star against that enormous surface gravity. But as a result of this implosion, the original magnetic field of the progenitor star is now amplified to enormous values of the order between 10 to the 4 and 10 to the 11 Tesla. So it's about 1 trillion times stronger than Earth's magnetic field. And this is just basically conservation of magnetic flux in this implosion process. The magnetic flux is conserved, and the original magnetic field is then obviously amplified to these enormous values. We also think, in terms of our models, that the interiors of these neutron stars consist of exotic material, basically a superfluid of neutrons, some superconducting protons, and the pressure is provided by these degenerate neutrons. So this is obviously based on models, depending on and this cooling curve that you see there in this region shows us that most probably the interior consists of very exotic material and not just normal baryonic matter that we are used to, and that the people can deduce from these cooling curves. So like I've mentioned, the interior, we think it is the density is obviously enormous. The density is the same as the density of an atomic nucleus, about 10 to the 15 grams per cubic centimeter, or 2 times 10 to the 14 to 10 to the 15 grams per cubic centimeter. This is the same as the density of an atomic nucleus. And as a result of this high density and crystalline structure, there's very exotic particles that you can find in this inner region according to the models. So they think that you have electrons that can interact via quantum processes, photon interaction over very long distances, compared to the lattice spacing inside this neutron star, which basically results in the material, these Cooper pairs, to behave like bosons, and they move inside this structure like a superconducting superfluid. A superconducting superfluid has very interesting quantum properties like no viscosity at all. That is very interesting, just to study the quantum processes of this exotic material there right at the very center of these exotic objects. You will remember that I've mentioned earlier that in the supernova explosion, enormous amount of neutrinos are released. And there was a supernova explosion in the Magellanic Cloud. I think it was in the Large Magellanic Cloud, if I remember correctly, with a distance of about 180,000 light years, that we were detected in 1987. And there was a very distinct neutrino signal. Just a couple of neutrinos that were detected. Remember, since the star exploded 180,000 light years from us, these neutrinos got dispersed into space, and only about 12 of these neutrinos moved through the Earth, right through our neutrino detectors in Japan. And based on the spread, the time spread of this neutrino signal, they could deduce the mass of the neutrino to be less than 30 electron volt. Up to that stage, 1987 up to 1990, it was not even sure that the neutrino had any rest mass at all. But this dispersion in the neutrino signal told us that there is a mass, and that the mass must be less than 30 electron volt. So this detection of the neutrinos was fundamental in the sense that it shows us much of the properties of the neutrino, and it helped us also to constrain the mass of the neutrino to less than 30 electron volt. So how do we detect these neutrinos? These neutrinos, since they don't interact with anything, they go right through the Earth. In fact, the neutrino can go through a layer of lead up to a few parsec thick without interacting with the lead nuclei in its path. So you can see from that that there's basically no interaction between these neutrinos and normal matter. But we can pick these, or we can detect these neutrinos by enormous water tanks. This is the Kamiokande detector in Japan. It's just an enormous tank filled with clear water, distilled water. And the sides of this neutrino detector is sort of covered with photomultiplier tubes. Each of these photomultiplier tubes are is so sensitive that they can detect a burning candle at the distance of the moon. That is basically how sensitive these photomultiplier tubes are. And there are thousands and thousands of these photomultiplier tubes. So the way in which they detect a neutrino is if the neutrino moves through that water, the neutrino actually moves through water with a velocity faster than the speed of light in water. So it's not violating any physical law. We know that the speed of light is a maximum if light propagates through a vacuum. But if this neutrino moves through water with a velocity greater than the speed of light in this water, it produces a light flash called Cherenkov light. And this Cherenkov light flashes can be detected by these photomultiplier tubes, and they can also reconstruct the path, in other words, the direction from the incoming neutrino. And recently, they have found a way to make these neutrino detectors even more sensitive by adding gadolinium. So these gadolinium is a rare earth metal, and about 13 tons of gadolinium compound have been added to this enormous body of water. And obviously, this gadolinium has the property of interacting with neutrinos. So what you get is, if you get an electron neutrino that enters the water, that neutrino can obviously can interact with a proton. So in that process, it emits a positron particle, and neutron is formed. That neutron is absorbed by the gadolinium, producing two gamma rays. So obviously, when you get those two gamma rays, you just know immediately you have detected a neutrino that moved through that detector, producing a neutron that was absorbed by the gadolinium, producing two gamma ray flashes. So when they get these two gamma ray flashes, zoop, zoop, basically immediately after one another, then they knew that they have detected a neutrino, and that is how they basically increased the sensitivity of these neutrino detectors to detect these neutrinos these days on a routine basis. I've mentioned earlier the conservation of magnetic flux amplified the magnetic fields of these neutron stars, but the conservation of rotational angular momentum also results in this compact star to spin quite rapidly. So the end result is a very fast rotating compact object with an enormous magnetic field. And obviously, when you have that, the combination of rapid rotation with a very strong magnetic field, according to the laws of electromagnetism, especially Faraday's induction law, you get you can get the generation of very strong electric fields. So this is just the two animations that I found on the internet to show you what the end result is if you have a moving magnetic field combined with a conductor. So if you have a magnetic field that moves in relation to a conductor, then you have basically a changing magnetic flux. If you have changing magnetic flux, you induce an EMF or a potential difference that can drive a current. And that is obviously the basis of the electrical motor as well. So this is electromagnetic induction. If you have a fast rotating magnet, you can see that you induce enormous electric fields. For example, if you have this conductor and you just have a normal fast rotating magnet or a rotating magnet, that rotating magnet obviously interacts with the free electrons, the conduction electrons in this metal, and producing currents that flow on the surface of this conductor. And this surface currents obviously produce their own magnetic field that provides that distortion that you can see there. So the message is, if you have a rapidly rotating magnetic field combined with a huge population of electrons, you can get electric fields that can obviously produce surface currents, and these currents can obviously provide that distortion. So this is basically to show you what we have. We have a very compressed compact object with a magnetic field, and it rotates very rapidly. The electric field that you can get there along the magnetic field lines depends obviously on the rotation velocity as well as the magnetic field strength. So this basically gives you the electric field, and that electric field is very strong. This ratio that you see there is the ratio of the electric field to gravity on the surface of these neutron stars, and you can see that the electric field is about a few million times stronger than gravity, and this results in the electric field to pull out charges from the surface crust and accelerate these charges along the magnetic field. And obviously, when you have these charges that accelerate along the magnetic field, you can get high energy emission through curvature radiation or synchrotron radiation. So just to show you the enormous potentials that these objects can produce, potentials of the order of about 3 × 10⁻16 volt. So I've also summarized it here. So this process is quite familiar to us. Whenever you have a rotating magnet, And the typical magnetic field inside these bicycle dynamos is between 100 to 1,000 Gauss, and they can produce currents that can obviously power a light. That is what you will find in bicycles. In neutron stars, you can have magnetic fields between 10 to the 12 and 10 to the 13 Gauss in strength. These objects rotate very rapidly, so the potentials, the electric fields that are generated is enormous, reaching values up to 10 to the 18 volts. So that is staggering. For white dwarfs, on the other hand, these objects can rotate on timescales between seconds and hours. The magnetic fields between 10 to the 5 and 10 to the 7 Gauss, which can also give you potentials between 10 to the 14 and 10 to the 16 volts. So you can see that even these white dwarf stars have the potential to accelerate charged particles to enormous energies. So the high energy particles that we detect from space, in this region of this, what we call the cosmic ray spectrum, all these particles are most probably produced by fast rotating neutron stars and maybe even fast rotating white dwarfs, producing charged particles with energies up to about 10 to the 16, 10 to 10 to the 17 volt. Compare that to the highest energy achievable by the Large Hadron Collider, which is about 10 to the 12 volt. You can see that these cosmic powerhouses are much more powerful than the most powerful particle accelerator we have here on our planet. So this is just basically a picture of this Large Hadron Collider with a circumference of about 30 kilometers or so there on the border between France and Switzerland. So the energies that that can be achieved by the Large Hadron Collider is if you have particle beams that are colliding, proton beams that they smash into one another. The energy in the center of mass reference frame is about 14 tera electron volt. So that is enormous. Just to give you an idea of how high that energy is, the energy of a normal optical photon that we can see with our eyes is about 1 electron volt. And this is about 10 to the 12 times higher. So you can see that even the Large Hadron Collider has the potential to accelerate particles to enormous energies, to produce obviously energy in the center of mass frame of about 14 TeV when these beams are colliding. Now, these rapidly rotating neutron stars have obviously an enormous amount of rotational kinetic energy as a result of the high moment of inertia of these objects. And obviously, these objects rotate slower with time because they radiate energy through magnetic dipole radiation. So the power in terms of radiation that you can get from magnetic dipole radiation is enormous. But these objects also spin down. In other words, they rotate slower with time. So you can see the total luminosity that you can get from the Crab pulsar in the Crab supernova remnant, which rotates 30 times per second around its own axis, is about 5 times 10 to the 31 watt. That is about 150 times higher than the luminosity of the sun. And over 1 year, the spin rate changes by about 0.04% as a result of this energy loss through magnetic dipole radiation and also charged particles that it accelerate outward in the form of a relativistic wind. So why are they called pulsars? Well, if you have such a fast rotating compact object with a high magnetic field and enormous electric fields there that rip charged particles like electrons out of the crust, accelerating it outward, producing radiation through synchrotron radiation, if that beam of radiation sweeps across your line of sight, you only see a pulse of radiation, and that is why these objects are called pulsars. So just to show you, it's basically a cosmic lighthouse. It is rotating fast, and if that beam of high energy emission sweeps across your line of sight, obviously you see a pulse of radiation. So that is why these objects are called pulsars. So this is X-ray and an optical photo of the Crab supernova remnant with the central engine, the pulsar there in the center. It is obviously highly slowed down, but you can see the energy that is radiated away and carried away and pumped into this nebula when that rotating beam sort of sweeps through that nebula, and the particles, the charged particles, having enormous energies, are pumped into that plasma, and you can see the energy that is carried away in terms of the outward propagation of the shock wave that is carried through this remnant. So this shows you the pulsed emission of this fast rotating neutron star and how that interacts with the medium. So this is a photo of the Crab supernova remnant, that inner region showing the pulsar. You can see that jet of high energy emission that is produced. And if you look at the remnant, supernova remnant, with an optical telescope, you see this, and as I've mentioned earlier, all this emission is basically the result of synchrotron emission of superrelativistic electrons that have been pumped into this remnant by the pulsar. Those electrons are trapped into the magnetic fields. They cannot really escape, and they basically power this whole remnant through synchrotron radiation. So this is an image by the Hubble Space Telescope. So all this emission that you see there is basically the result of synchrotron emission of these electrons. So where do you find the Crab supernova remnant? That is just Messier 1. Close to, well, not too far away from the Hades, where you have Aldebaran in Taurus, the bull. There is M1, not too far from Orion either. So this is the supernova remnant, and that is what you will see with even a small telescope. If you have a 20-centimeter telescope, you can basically see the synchrotron radiation and zoom into that central part where you see the central engine, the pulsar that is powering that whole remnant. What you can see here is the total energy emission over the whole range of the electromagnetic spectrum, from radio frequencies up to the highest energy gamma rays, that is all produced by the superrelativistic particles that is produced in that pulsar through this particle acceleration process. So how do we detect? We know how to detect radio emissions, obviously with radio telescopes, optical emission with optical telescopes, X-ray emission with X-ray telescopes. But how do we detect these high energy gamma ray emission? Obviously, the gamma ray window we can stretch from about a few GeV all the way up to 30 tera electron volt. There are various processes in which we can detect the gamma rays. With gamma ray energies less than 30 GeV, we can use typically the Fermi gamma ray satellite. That is how we detect gamma rays in this energy regime. In the energy regime between 30 giga electron volt and 30 tera electron volt, we make use of atmospheric Cherenkov detectors. So if an incoming gamma ray moves through the atmosphere, we basically produced a cascade of secondary particles, and as those particles propagate through the air with velocities greater than the speed of light in air, they produce Cherenkov light, which can be detected. And for energies greater than 30 tera electron volt, we make use of these water Cherenkov detectors. There's one big water Cherenkov detector in Mexico, but also high up in the Himalayas. So the gamma ray telescopes, the air Cherenkov detectors that we are involved in, is the HAC telescope in Namibia, about 120 kilometers southwest of Windhoek. But there's also another big telescope that is currently coming online, hopefully in the next couple of years, the Cherenkov telescope array. We are also part of this collaboration, and hopefully in the next 5 or so years, we will at least have the northern leg of this Cherenkov telescope array on La Palma, which operational. So we are all looking forward to that. You can see the sensitivity curves of CTA, the projected sensitivity curve of CTA compared to HAC. The lower this curve is, obviously the more sensitive this telescope is. So you can see that CTA will be much more sensitive even than HAC, which is currently the biggest and most sensitive gamma ray telescope on the planet. So just to show you again the total energy that is emitted by this pulsar in the central parts of this supernova remnant. You have the energy emission in radio, which is produced by relativistic electrons with energies of about 10 giga-electron volt. Optical photons are produced by electrons with energies of the order of 300 giga-electron volts, typically what we call Lorentz factors of the order of 10 to the 6. The soft X-rays are produced by electrons with energies of about 10 tera-electron volt. And you can see that is typically the energies reachable by the Large Hadron Collider. And these high energy X-ray photons are produced by superrelativistic electrons with energies of the order of 100 tera-electron volt. But since you have optical photons and high energy electrons, you have another process that comes into play, and that is the so-called inverse Compton scattering process. So this inverse Compton scattering process is where you get a superrelativistic electron that scatters an optical photon up to higher energy gamma rays. And the energy of the scattered photon is about gamma squared times higher than the energy of the initial photon. So if you have an electron with a Lorentz factor of about 1 million, interacting with an optical photon with an energy of about 1 electron volt, the end result is basically a high energy gamma ray with an energy of about 1 tera-electron volt. And obviously, in this energy regime, we can only detect these gamma rays using atmospheric Cherenkov detectors. Okay, so to conclude, I want to show you also some of the results of two fast rotating white dwarfs in binary systems. The one is called Quera, where you have a white dwarf star with a very fast rotating white dwarf with a short rotation period of about 33 seconds. So imagine this, you have an object as big as the Earth, weighing about as much as the Sun, that spins around its axis once every 33 seconds. That is staggering. And this white dwarf is also orbiting the secondary star in the time of about 10 hours. So the fast rotation period of this white dwarf has been detected in optical, with optical telescopes, and these two peaks that you see there, the first peak there is at 33 seconds, and the second peak that you see there in this power spectrum is at half of that. So there you see basically two poles that you can pick up in optical frequencies. But you see there is actually the rotation period of this white dwarf. When I started to study this system when I was a student, they were looking at it in radio frequencies using the VLA telescope in New Mexico. Enormous fluctuations in the radio intensity was observed, and they predicted that this fluctuations in the radio is a result of relativistic electrons that are produced by obviously some process in the system. We know now that relativistic electrons are produced by the fast rotating white dwarf. In that era, we also had a gamma ray telescope close to Potchefstroom at Nooitgedacht. It's basically on the rim of the Vredefort crater, where we also detected gamma ray signals at the spin period of the white dwarf, 33 seconds. So we were one of the first groups in the world to detect gamma ray emission at energies higher than 1 tera-electron volt of this fascinating object. We also detected with a group in Australia short gamma ray flashes, and if you make models to explain these gamma ray flashes, you will see that enormous amounts of energies have been released over a very short time scale. And all that energy is pumped into gamma rays. And these gamma ray flashes have been detected by two independent groups. Our group at Potchefstroom, and the other group which basically the Durham group in the United Kingdom, but they have their telescopes at Narrabri in Australia. Then there's also an interesting system that have been discovered recently, AR Scorpii, that consists of a white dwarf orbiting a M-type red dwarf star. The orbital period is about 3.5 hours, but that white dwarf spins around its axis once every 120 seconds. And here you can see the pulses, the pulsations measured in various wavelengths, infrared all the way up to radio wavelengths, but you can clearly see the pulsation period of the fast rotating white dwarf. In this case, the rotation period is about 2 minutes. With our telescopes at Boyden, the Boyden Observatory, my student observed the orbital period of this system, 3.5 hours. And this enormous spread in the data points is not due to bad measurements. You can actually see the enormous pulsations at the spin period of the white dwarf, and you see both peaks. In other words, you see both poles of the white dwarf spinning through your line of sight. So that enormous spread that you see there is nothing else than the pulsation period of the white dwarf that you see there superimposed on the orbital period. So that is what we observed with our telescopes. Helene also continued to take spectra with the 1.9 meter telescope at Sutherland, measuring the orbital period. And the orbital, the radial velocities follow the orbital period of the secondary star, and it shows basically that all these emission lines that you see there is basically produced there at the inner edge, inner face of the secondary star, and which is now being illuminated by this beam of relativistic particles that pump that region and obviously excites the gas there, producing these emission lines. And obviously this emission lines follow the orbital period of the secondary star. So this is what we also, that Helene measured with her observations at Sutherland. So you can see there also the pulsations of this white dwarf. That you see there is basically the rotation period of the white dwarf. And the mechanism that produces the radiation, we believe, is synchrotron radiation, where you have relativistic electrons trapped in a magnetic field, spiraling, producing radiation. And obviously, since you have a pulsar-like emission process, you basically have that beam that swings through your line of sight regularly and producing these pulsations. So the total energy spectra of the two sources, AR Scorpii and AE Quaera, is this. And you can see emission is produced over a wide range of frequencies in both sources. And the interesting thing is that in both these sources, the emission is not produced by mass accretion onto the surface of the white dwarf, because AE Quaera has a very efficient propeller process. It is driving away all the material from the system, so nothing gets accreted onto the surface of the white dwarf. So all this emission is produced through various processes, but none of it via mass accretion onto the surface. And the same also for AR Scorpii. So we observe both these sources using the Meerkat telescope. So AE Quaera was observed at some point. I can't remember the dates here, but I think it is, let me just see, let me just go back one more. So these observations, the times of the observation, I think it was scheduled in 2018 or so. It was just in that, I think, pre-COVID period, where we used all 61 dishes, providing several baselines that obviously can give you enormous resolution. So if you look at the resolution that you can obtain with all that number of baselines, there you can see that A Quaeri is basically observed as a well-defined point source. And that is basically the result of the spectacular resolution of the Meerkat telescope as a result of that various baselines that you use to observe it. So if you take a power spectrum of the emission, you can see here clearly we have detected the spin period of the white dwarf, and that was the first time that was observed in radio frequencies, and that is the result of the spectacular resolution and sensitivity of the Meerkat radio telescope, where we were the first people that detected the spin period of the white dwarf. And the spin period, the emission, is nothing else than synchrotron emission of highly relativistic electrons that are accelerated away from the polar caps, and obviously producing radio emission via this pulsar process. And this power spectrum shows us the spin period of the white dwarf. This is just basically where the data lies in terms of the flux density versus frequency for Meerkat is there. And you can see that as a result of this spectacular sensitivity, we could basically go down that low in terms of flux density at frequencies of the order of 1 gigahertz. And that is all in all the result of the spectacular sensitivity of Meerkat. The same also for AR Scorpio. That was also observed 2020, 3 observations. And we also detected the spin frequency of the white dwarf. But in this case, we were not the first to detect that. There were another group that detected and reported the spin period of the white dwarf of AR Scorpio. So for AR Scorpio also, this is where the Meerkat flux data points lie. Okay, so we also had a long baseline in gamma rays with the Fermi telescope, more than 10 years. And combining the 10-year data sets for AE Quaeri and AR Scorpio, we could detect for both these sources the spin period of the white dwarf with the associated first harmonic. So that is the signal of the 33-second rotation period, and that is the second pole that come into play. So obviously we were the first to detect this signal also of AE Quaeri in gamma ray frequencies with the Fermi gamma ray telescope. And also the same for AR Scorpio, combining the 10-year data set and taking a Fourier spectrum of the emission, we could detect, albeit at a lower significance level, the spin period of the white dwarf for the system as well. So for both these sources, we could see with our observations in radio and gamma ray that we could clearly identify the spin period of the white dwarf. For radio, it is produced by synchrotron radiation, and for gamma rays, the pulsed emission is most probably, and I've indicated it in a very recent paper that is published in the journal Galaxies, that the emission must be produced by curvature radiation. So curvature radiation is just when you have very high energy electrons following, and the electrons have such high energy that it basically follows the magnetic field lines, the curvature of the field lines. And since the electron move in a circular orbit along the field lines and not around the field lines, the emission is curvature radiation. And I've also made predictions in terms of where that emission should peak. And the predictions match our observations that all gamma rays, pulsed gamma rays at gamma ray energies below 10 giga electron volt should be produced by this curvature radiation process. So hopefully with this, I've showed that these objects are fascinating. Fast rotating neutron stars can produce emission up to the highest energy gamma rays, exceeding 10 to the 12 tera electron volt. A typical example is the Crab supernova remnant. And with these two objects, I've showed you that fast rotating white dwarfs with strong magnetic fields are equally interesting. And that can produce through processes like curvature radiation, gamma rays with energies peaking below 10 gigaelectron volt. For the emission that we detected earlier with the Potchefstroom telescope in energies of about tera-electron volt, we believe that that emission is the result of protons that are accelerated along the magnetic field lines, colliding with gas and producing gamma rays through the decay of pi-0 mesons. So that is basically the presentation. I hope at least it gives you something to think about. And if there are questions, I will be happy to answer questions if I can. So yeah, please, and thank you again for inviting me to give this presentation.
Thanks very much, Peter. That was really fascinating, extremely mind-boggling. Quick question: what's the closest white dwarf to our solar system?
Well, the closest one I'm not so sure, but Query, that system is about 100 parsec away from us, and that is actually quite close. So that is one of the closest white dwarf binaries that we know of.
What's that in light years?
Say again.
100 parsec is how many light years again?
Well, 1 parsec is 3.2 light years, so it's about 300 light years.
300, okay.
Roughly,
so we can send our Minister of Electricity there with extension.
Yeah, we can send him to the center of the Milky Way galaxy also, as far away as possible.
Fascinating. Anybody now with questions? I'm sure there must be some.
Okay, Pete, one small question from my side. You mentioned the production of iron from stars. How long normally does it take for nuclear fusion to produce iron if you start off with hydrogen burning and then end up with iron in the core? I mean, for a typical star, it would
these processes. This is a very good question. So for these massive stars, they run through their nuclear processes over timescales of about 1 million years or so, less than 10 million years. So in other words, you start off with proton fusion, and then you produce heavier elements. And that last phase where you burn, let's say, elements just slightly lighter than iron to get iron, that process lasts about a day to build that iron core. A day to less than a day. It is just mind-boggling to think that last process occurs so rapidly to get that iron core, and then obviously everything shuts down from that point on. The whole system basically collapses.
So it's actually quite fast. I mean, if you
yes, absolutely. That last phase to produce iron, basically a day or so, and the implosion of that core occurs on a time scale of 1 millisecond. Poof. It's just basically instantaneous.
So basically, I'll have to look at a new perspective with the motor car that I drive to look at where the iron is coming from for producing the motor car.
Yeah.
Just another question, if I have time. You mentioned infrared in one of your slides, just in passing. Do you think the Webb telescope might contribute or something to your investigations in high energy region, or is that a little bit far-fetched?
No, I think definitely. I mean, the James Webb telescope can reach these white dwarf systems in regions, let's say, inside molecular clouds where they are hidden. So normally normal optical light cannot penetrate these molecular clouds, and we think that, and also in these dense environment, star-forming regions, there may be, like for example, that cluster that I showed you. There may be thousands and thousands of these white dwarf stars, but they may be hidden behind gas. So with the James Webb telescope, I mean that telescope can penetrate these layers of gas to basically get to the white dwarf stars that are hidden behind. So obviously, I think there's definitely a lot of scope for the James Webb telescope to make enormous sort of contributions in this field.
Thanks, Piet. That answers my question. Thank you very much.
All right, anybody else?
Pierre de Villiers, I just want to congratulate you on an absolutely fascinating talk. You conveyed a lot of highly technical information or data in a very entertaining manner. I don't know if you've got young grandchildren yet, but if you do, you'll be a very good bedtime storyteller. Your description of the breakdown of the supernova explosion via energy drainage was absolutely superb. I've never heard that before. And I must also admit to the ignorance of not realizing that the supernova 1987A actually imposed the upper limit to the mass of the
neutrino.
Anyway, Peter, thank you very much. It was excellent. Most enjoyable.
Thank you very much. I appreciate
I
it.
see David and Elaine have got a hand up.
Yeah. Sorry, first of all, thank you for a lovely lecture. I think I will be watching it very, very many times. And then I was just wondering, you showed the binding energy curve, and I've always been fascinated by that strange dip between hydrogen, helium and lithium. It's suddenly the binding energy goes up, and then it has this dip, and then it kind of grows up very gradually all the time. And I just wonder what the significance is of that.
That is basically the result of the nuclear, the structure of the atomic nucleus of those elements. And in other words, what the energy shells of the nucleus is for, if you compare, for example, helium with lithium and some of the other heavier elements. So that is the result of the structure of the nucleus and the energy levels of the nucleus.
Thank you.
I think it's a good thing that this is on Zoom and you're recording it, because this will have to be watched a few times to take a bit more of it in. Quite a lot presented there, and I think I'm quite pleased that Pierre mentioned that info that he hasn't heard of before. I'm sure there's lots that I haven't heard of before that I need to look at again. Any more questions? Yeah. Many thanks for this. Sorry, Josta's got a raised hand.
Good evening. Thank you for a wonderful presentation. Just like to know, how do you separate on your the diagram that you've got right there? Right now, the one
Sorry, can I just
the period of the rotation compared to that of the white dwarf. How do you know which is which?
Because we know from observations in different parts of the electromagnetic spectrum, like for example radio and optical and X-rays, what the rotation period is. So in other words, for HAC query, optical observations and X-ray observations tells us exactly that the rotation period is 33 seconds. So if you want to convert that to frequency, that gives you about 50 millihertz or so. For AR Scorpio, the rotation period is about 117 seconds, also from optical and X-ray observations. And if you convert that into frequency, that gives you that's something just slightly above 8.5 millihertz. So that is how we know that is the rotation period of the white dwarf. In this case, it's the rotation period of AR Scorpio, and in the previous case, that 50 millihertz, that is a rotation period of HAC query, with the associated first harmonic. And there was a second pole. In other words, you see both poles producing emission swinging through your line of sight.
Okay, thank you so much.
All right, thanks. Any more? Yeah, this is a great presentation with some great slides, everything very clearly presented. So yeah, it would be very nice to go through this again on the YouTube video. Definitely be doing that.
But thank you again for this invitation. I really appreciate this. And luckily I could give the presentation. I know it was scheduled about a month earlier, but unfortunately I had to undergo back surgery in the meantime. So but luckily I am fit enough now this evening to give this presentation. It is a great privilege for me. Thank you very much for this invitation.
Much appreciated and fantastic. Okay, any more questions? All right. Joost says, thanks so much for a great presentation. Privileged to have been able to be on the chat. Okay. Thanks very much for everybody's attendance, and I'm pleased to have met you. And I think it was a really, really interesting presentation. Once again, thanks. Maybe we can do a physical presentation when you come to Amanus to play golf or something one day.
I will be very happy to visit Peter there at some point. And yes, by all means, if I'm in that part of the world, I will be more than happy to give a face-to-face presentation.
And we got some good back doctors here too.
Yeah, I can imagine that. Yeah, thanks.
All right. Wonderful. Thanks very much for a fascinating evening. Nobody else got anything, other questions, and we'll wind it up.
Thank you very much, and Piet, for an excellent talk, and good night, everyone.
Good night.
Baie dankie Pieter, dit was lekker om goed na jou te luister.
Baie dankie. Plesier was myne geweest. Baie dankie.
Okay, thanks very much. I'm going to end the recording then. Switch off. Night, everybody.
Bye-bye. Good night.
Yeah, good night, everybody.
Bye-bye.